Let's take a look at an example for simple harmonic motion and get used to some of the terminology. So here we have a mass, a body hanging from one end of a vertical spring. The distance between 2 points at which the speed is 0 is 7.5 centimeters. Okay, and so the speed would be 0 at the very top and at the very bottom as it's changing directions. And so the distance between those two is 7.5 centimeters. So for part A, when we're asked to find the amplitude, capital A or x sub m, is not 7.5 centimeters. It's going to be half of that because an amplitude is measured from the center or from the equilibrium point. So our amplitude would be 3.75 centimeters or 0.0375 meters. The other information we're given is that the time taken for the body to move between those 2 points is 0.17 seconds. Okay, so that actually only represents half of the motion because the full motion is when the object returns back to its original position, completes one full cycle. And so to answer part B, we'll first find the period by multiplying this time by 2, so 0.34 seconds. And then we can go ahead and find the frequency. Now, there is an angular frequency and there is just frequency. If it doesn't say angular frequency, it means F. All right, so this is looking for F, which is 1 over the period. So 1 over 0.34 seconds. And so we get 2.9, and then this is measured in hertz. 1 over seconds is called a hertz. You might recall that from the first year class. The maximum acceleration of the object is just a pure calculation. So we'd found by looking at the sine and cosine functions how this term capital A omega squared kept showing up in front of the acceleration, the sine or cosine. That represents our maximum value of acceleration. And so we need to know the amplitude and we need to know omega. I don't know omega, but I know sort of other parts of omega. Let's just substitute in a formula. Omega is 2 pi times the regular frequency. And so if I can just use this frequency value I had before, and so we can say 0.0375 meters times 2 pi times 2.9 hertz. And again, a hertz is a second to the negative 1. I'm going to put it in like that so we can see the units, so that you can see how this is meters per second squared. It is a linear acceleration. Let me get to my calculator here for a second. All right, so I'm getting about 12. We'll call it 12.5. I have room here, 12.5. And again, that would be meters per second squared. That's a linear acceleration corresponding to a force.